understood those assignments and you solve yourself or not. So take the assignments very seriously. That is having very heavy weightage in this semester. The assignments may contain some small programming part also, so that we'll see how we can able to implement that. So either in the MATLAB or there are open source like Scilab is there, that kind of thing. You can be able to use it. We will introduce those things in due course in the course. So what I will do now, I will start a particular chapter, the first chapter of the book which I have mentioned. So I hope you can able to see the this particular PPT, Panta.
Yes, sir.
Yeah. Okay.
Yes, sir.
So first thing is the system. When we are talking about system for this particular course, we talk about the dynamic system. Dynamic system means in which we have forces which are dynamic in nature, that is, they are time dependent. And when we're talking about system, in system there can be several components which will be connected together and they will act as a whole when a particular force is applied in that particular system. So like you can see a railway wagon. This is a dynamic system in which several forces may come. The most common force is the engine which it pulls to this particular wagon. You must have seen that those forces, because of the different wagons are connected to each other, the force transmission is not static one. Dynamically it changes because of the motion of the wagon. In this, there can be other kind of forces on the rail, because rail is smooth, but still there are having roughness even in the wheels. So when this wagon moves on to the rail, there will be, due to the roughness, there will be various kind of motions. Even when there are rail brakes are there, where there are gaps are there between the rail, when these wheels go there, there will be some kind of jerk will experience each of the wheel. So several kind of forces are coming into this. So how to find what kind of motion will take place of this particular wagon because of that force could be our concern. So this is a dynamic system in which where flexible elements are there, because here wheel is connected with the wagon by springs. So during motion, they will be having relative motion. As such, the wagon is rigid, but wagon can have motion in up and down motion, or it can have sideways motion also, because of the when it is turning in a curved track, or this particular wagon itself can have a tilting motion in 3 axes. So you can see that this particular system is quite complex to analyze as such. But then, because we need to, as engineer, we need to find solution for this. So we will try to idealize this in some way, so that we can able to find out some basic dynamic characteristic of this particular system, so that we should able to use this in the track without any problem. So how we can able to analyze such system, complex system? So as I mentioned, in the system there are various components, and each component is having some property. Like if we are talking about wheels is having inertia because they're moving, so rotary inertia also will be there. The wagon, the top part will be having mass that will also be having various kind of inertia. In between them, there are leaf springs are provided. So the coil springs are provided. They have flexibility or the stiffness of them. Even some kind of dampers are provided between the wheel and uh, the body of the railway wagon so that undue vibrations, if it is taking place, that should damp out. So in dynamic system, these are the different system property we need to identify. What is the inertia of the various components, uh, whether some elements are having some flexibility or we have some kind of uh, damping characteristic. Okay, and so we need to have some assumption regarding that. Like if we are saying, okay, this particular the our body is rigid, but actually is not rigid. So we need to make some assumptions, engineering assumptions. By that way, we can able to say, okay, this particular uh, the body of the wagon is rigid. Similarly, regarding the wheels, we can say this is rigid, but actually some deformation may take place. But for simplification of the analysis, we can ignore those small deformations. But finally, we will get some uh, meaningful dynamic behavior from this. Then we can say that whatever the simplification which we have made is acceptable. If we are not getting a particular behavior which we are seeing in actual wagon, then we need to see what assumptions we need to relax, what assumption we should relax so that we can able to mimic the actual physical behavior, or like I'm talking about behavior means the vibration response or the displacement or velocity of the wagon or the acceleration of the wagon to be as per prediction from the theoretical model. So once we are making some assumptions using law of mechanics, we can able to make some kind of governing equation in the form of differential equation that is called mathematical model. Uh, so that mathematical model we can able to solve, and that will give some kind of uh, response, either displacement if you are interested, or velocity of the system, or acceleration for a given force. So force is there in the system property is there, and we are finding the response of that. So how we can able to do the simplification? In that also there are two different approaches are there. One is the discrete system. I'll talk more about this also in the present lecture, and the continuous system. Okay. So I think some questions are there. If some question is there, I think I will take up at appropriate time, then you can ask. Okay. So at present, Pantha, you have anything?
Sir, means the recording stopped once, but I have started it. That's why
okay. Okay. So keep looking into that. Okay.
Yes, sir.
Okay. So as I mentioned, there are two approaches. One is the discrete system, and another is the continuous system. So in discrete system, what we assume that like if we are taking a particular example of a wagon, the top surface we can assume that this is having only mass, is having no stiffness. Spring, which is there, which is the suspension system, will be having the spring action and the damping action. So if you see here, mathematical model. So here a particular behavior is being analyzed, that is the only the one direction motion along the direction of the rail, not the up and down motion is being analyzed here. So that is this simplification we are making. Okay, we want to analyze this particular wagon having some mass. Here between the two wagons there are coupling, and in the coupling not only the spring is there but damper is also there between the coupling. So here as such, because we want to analyze in the axial direction motion how this wagon will be having. So the suspension system has been taken as a rigid. The whole wagon has been taken as a rigid and is having uh, mass only. So there is no flexibility in the wagon itself. Only this is coming from the coupling. Stiffness and the damping is coming from the coupling. So now some force which is time dependent is applied to this particular wagon. So we want to analyze what will be the uh, response of this particular wagon because of that force. So here force is time dependent because we are analyzing the dynamic system. So correspondingly, the response also, the displacement of the wagon also will be that will be time dependent. So here there are three property in the dynamic system, especially in the discrete system, is having mass. So once we are saying a particular body is having mass, so we are assuming that there is no stiffness in that. When we are saying a coupling is having damping or stiffness, then is having no mass. So that kind of assumption is called discrete system. Uh, this will be more clear, the discrete system and the continuous system in the next slide. So please the time here. Okay, so the equations which comes for that kind of system, because that is a simple single degree of freedom system, which you have already studied in your dynamics summation course. So mass into acceleration. So this is the inertia force, damping into velocity. This is the damping force from the coupling, and stiffness into the displacement. That is nothing but the stiffness force or restoring force. So these three forces, inertia, damping, and restoring force, are balanced by the external force or equal to the external force. So this is a typical, I think, equation of motion you write. Often this time derivative we write in terms of double dot. So here second order derivative with respect to time is there. So we are representing that as a double dot. So this is just a representation so that our equation become more compact. So double dot represent derivative twice with respect to time, and single dot represent derivative with respect to time once. So this is the equation of motion for discrete system. So here if you see mathematically, m is a constant, c is a constant, k is constant. So these are all having constant coefficients. So in discrete system, this behavior you'll see that all the coefficients will be constant. They will not be depend upon the either independent variable or dependent variable y. So m, c, k are not function of y, or neither they are function of time. And this differential equation is ordinary differential equation of second order. There are other differential equation which we call it partial differential equation, that we'll see that will be coming in the other systems like continuous system. So when we are talking about the continuous system, so this is a typical another example of the continuous system. So this you can think as a maybe the wing of aircraft. So it is fixed at the body of the aircraft, and this is the wing, and is having some kind of force which is coming for this particular case the axial force again in the same direction as the wing direction. So this particular wing is having, now you can see the, as such, you cannot see any component within the this particular body. So this is a solid body, but is having flexibility in the axial direction. And because the variation of the geometry is there, so mass is also changing continuously along the x direction. So this is the typical behavior of the continuous system, in which the mass will depend upon the x, or the dependent variable x. So like here it was constant in the case of discrete system, but here mass is depend upon this particular spatial coordinate x. And similarly, the stiffness also will change because uh, the geometry is changing. Okay, so you can see here it is written m function of x. EA is the Young's modulus into area of cross section. So that will define the stiffness of this particular body. So this will be also a function of the geometry, the axis x. Force which we are applying on this thing is also, not only it will depend upon the time, but also it will depend upon the x coordinate. So this is a typical continuous system, and equation of motion for such system is more complex. They are, now you can see the derivative with respect to time is there, as well as the derivative with respect to spatial coordinate x is there. So as I mentioned, the Young's modulus area that defines the restoring force or the spring force of that particular bar. So this is the elastic force. The whole term is elastic force. The derivation of this we'll see in due course. This is the external force. This is mass, which is function of x, and this is the acceleration. So this is the inertia force. Damping is not considered here, because in continuous system damping modeling is very difficult. So I will just ask, if you have any doubt on this, maybe you can raise hand till now, whatever I have covered, so that you are there with me. Otherwise, if you have any query, you can just raise your hand. I will try to answer your query. Any query till now? Okay. So, Jeevan,
Yes,
you
sir.
can,
Sir,
yeah.
here the mass is varying with respect to x. So can we have the continuous system where mass is varying with respect to time?
Uh, that is actually when it is like in rockets, when we talk about what happens
Yes,
in the
yes.
rocket when the
The
fuel is
fuel
getting,
is ejected.
yeah, fuel is, when it is burning, the weight of the rocket will reduce. Okay, so that is this is not continuous system, but in that the coefficients of the equation will be time dependent. Okay, so
Okay,
that
sir.
will be that we so time dependent coefficients in the equation will be there. Okay,
Okay,
and they're more difficult to solve. Okay,
okay. So it is not a continuous system.
these are our idealization. Okay,
Okay,
that, yeah, that is our idealization. If a continuous system can have time dependent thing, so that will be very complex. So both time dependent as well as the uh, spatial dependent. Okay. So that is more
okay.
difficult. So that is, that kind of equations we're not handling here. Just wait. Hello. हाँ मेरा भी क्लास में है. Hello. हाँ.
Yes.
So is clear?
Yeah, okay, sir. Yes.
Hello.
Yes, sir.
हाँ,
Yes.
Prashant.
Hello.
Prashant.
Yes, sir. Is from where we get that differential equation?
Hello.
Sir, I'm asking about from where I get that differential equation.
Yeah, at present I'm just showing you, we will derive those equations. No, we will derive those equations, will derive. In due course, we'll derive. Okay, at present I'm just trying to show because before going to that, we need to have some understanding of the how the system can be modeled. No, so that you have some physical understanding of that. No, because once we enter into those mathematics, then the physics will be lost and will be solving the mathematics only.
Sir, one more question. X
Ah.
and Y is taken in same direction.
X and Y
Is taken in the same direction. Bar.
no. Y will be because in this particular thing, X is this, Y will be in the other direction. But if we want to consider Y also, so instead of bar, we need to consider the plate problem. Plates. Okay. So that will be two-dimensional object. So here we are considering one-dimensional object. Okay. Fine.
Yes.
Yeah. Next. Swabhiman.
Yes, sir. So in discrete system, like you told a few minutes ago, that we are getting a fixed differential equation, and I just wanted to know that in continuous system, the differential equation that we are getting is for a particular point, or I mean, what is it means? Is it for a particular means we're taking an element at a particular distance, and that differential equation is varying along the length? Is it like that? Is it like that?
Yeah, actually, when we say governing equation, then it is for the system. Okay, system as a whole. So
Okay, sir.
So in continuous system, it will be valid for each and every point.
Okay, sir.
Because
Okay,
it's function of x. So whatever the x value you put, it will define that particular point behavior.
Okay, sir. Okay, sir.
So it will be representing the whole system, not particular point.
Okay, okay, sir. Yes.
Okay. Yeah.
Thank you, sir.
Okay. Swabhi, okay. Anyone? Swabhiman goes to Nikhil Kumar. Nikhil Mishra.
Sir, yes, sir. My question is that, sir, in a system like we direct using the
Your
similarly in
voice,
the continuous system.
your
Uh,
voice is breaking. Maybe
so,
you can write in the chat box. Okay, you write by the
sir,
time.
hello.
Your voice is not clear. You write in the chat box. Kunal, you can ask question. Kunal?
1 minute, sir.
Sir, could you repeat the mathematical equation of continuous system?
Yeah, I will repeat it. So this particular actually we'll be deriving all these things. At present, just I wanted to show how this equation will look like. Okay, so we are not deriving this equation. This is a simple. So you can see this is a partial differential with respect to x. So this particular term is elastic force because having Young's modulus and area other things. This is the external force, which is function of time as well as spatial coordinate. This is inertia, that is mass per unit length, and then the acceleration. So if you see this equation is you already solved in mathematics. If I drop the force term, this is a wave equation. Okay, so mathematically you solve this. Because how to correlate with the vibrations we are trying to see here. Okay.
Okay, sir. Thank you, sir.
So I think what about this question has come regarding the Sai Guru?
Sir, my doubt is regarding the continuous system. You have explained that a bar is subjected to an axial force.
Yes.
Sir, in what way there is an experience of vibrations in that case, sir, when it is subjected to an axial loading?
Yeah. So what will be there along the length of the bar? They will be having relative displacement.
Okay, sir.
Yeah. So every point will be having different displacement. Okay.
Yes, sir. Yes.
Yeah. So they will get stretched just like rubber.
But that is not vibration, no, sir.
But when the force is dynamic, rubber, if a block is there, and if you give axial force, they will be having vibrations.
Sir, you mean in the fatigue case or any cyclic load in such type of cases?
Yeah, like I gave the wings of the aircraft. So maybe wind is blowing in such a way that is giving a axial force.
Okay.
So
Yes, sir. Okay.
yeah. Okay. So okay, I think any other? What about Nikhil Mishra? He did not write the question. Okay, we'll take up his thing.
Hello.
Ah.
Hello.
Yes.
Sir, I am Nikhil Kumar Mishra.
Yes.
Sir, my doubt is clear. Actually, I want to ask how that the differential equation came. So that you said that you will derive later, sir.
Yes.
Okay.
Okay. I think
Thank
now
you.
all the queries are there because initially, definitely you'll be having a lot of queries because all of you have come with different background. So gradually, that's why I'm going slow at present. So now we know what is system and what is the response. So response is the displacement or velocity or acceleration. Okay. So that particular three things. Here you can see in the block diagram, there is a system characteristic, which is nothing but the system property. Maybe this is stiffness, damping, or mass. And in this system, we are applying some force, excitation force. And this excitation force will give some response in the form of displacement or whatever. So this is a block diagram of that particular system in which system characteristics is there, having stiffness, damping, and mass, and external force are coming, and because of that, corresponding response will come. Okay, so this is a typical block diagram of a dynamic system having excitation, system property, and response. The previous differential equation which we had, this one, okay. So because here you can see y is common in all three terms in the left side. Y is common in all three. So if I take out y out, so whatever is left out is this. So n double derivative of with respect to time, and c first derivative with respect to time and stiffness. So this is some kind of differential operator, okay, which we are representing as a the system property, which is containing the mass, damping, and stiffness. Okay, so this system characteristic, as I was mentioning, is represented by this differential operator, and different system will be having different such operators, especially for the continuous system, it will be different. So now systems, when we are talking about, some of you already mentioned that whether this mass property can be time dependent or the stiffness can be time dependent. So there are two broad way of classifying this particular system. One is the linear system and another is the nonlinear system. So in linear system, the dependent variable y, which is displacement, will be having power of 0 or 1. So that means only the this y will be having highest power will be 1. But in between, this also will not be there. Either it will be 0, that term will be constant, or 1. And when this is there, we have principle of superposition, which is will be valid. I'll be explaining what is principle of superposition. Then in nonlinear system, this dependent variable, the y, can have power anything apart from this. Like it can have y square term or y cube or y1, y raised to 1.1, or if there are more dependent variable like y and x, then we can have product of them. That is also a nonlinear system. And nonlinear systems are very difficult to solve. And in this particular course, we are not dealing with the nonlinear system. Even the time-dependent variable, the mass and stiffness, that is also we are not considering. Those equations are called parametrically excited system. So that also we are not considering here. Only the linear system having power 1. So I can go back to the previous equation. You can see here the power of y is 1, is having derivative with respect to x, but there is no y square term here anywhere. The derivative is having twice, but y is having single power. Similarly, in the previous here, y is having single power. Or here there is no power. So it's a linear system. Both of them are linear system. Okay. So how we can able to define linear system or linear equation, linear function or nonlinear function? So let us say we have one force applied to the system, and because of that we are getting the y1 displacement from that system. Because if you change the force, the response will change. So here you can see when we are changing the force, the response y2 is changing. So now y1 is this response due to the excitation f1, y2 is the response due to excitation f2, and g is the differential operator which I mentioned earlier, that is the system property. Now if there is a force, let us say a third force is there, which is combination of first force F1 and second force F2. So C1 and C2 are some constant. So this is the third force. So if we apply this third force to that particular system, so we will be getting y3 displacement, let us say. Okay, so this y3 displacement, if let us say it comes out to be summation of the one displacement, the first displacement multiplied by that particular constant, and second displacement, this should be y. I can do online itself. Okay. So this is a y2. So you can see that what is happening here, the first response, second response is giving us the third response directly by linear summation of that. Okay, so such kind of system is called linear system. But if this is not equal, like here, the y3 is not equal to summation of this response multiplied by corresponding force contribution, then this is a nonlinear system. So you can able to check that if we have some nonlinear function like x square or y square, these kind of things you cannot able to do it. Okay, so this is called law of superposition, in which we can able to obtain the any particular force response if he is having two components, by obtaining the response of individual component of the force and then adding them according to their weightage. Okay, so this is a linear system. Maybe after some time I will allow you to ask a question on that. Okay, so here you can see that if G is the system property, if it is nonlinear, then if you see here, if I am applying the G operator inside the bracket like this, if these two are not equal, then the system is nonlinear. If they are equal, they will be linear. Okay, and in nonlinear system, uh, that will not be dealing with there, but nonlinear system can be simplified by small motion assumption. How we can go to do it, we'll see with this pendulum example. But before that, let us see what kind of forces are there in the system. Because we have talked about the mass, we have talked about the stiffness, damping we'll talk in later, but what about the forces? What are the different kind of forces we can have? So there are two broad category of forces are there. One is the deterministic force and another is the non-deterministic or random force. What is deterministic force? A force which we can able to predict in the form of function, or we can able to specify at one particular time what the value of that particular force is there in a unique way. Okay, so if at t is equal to 20 seconds, that force is having 20 Newton. At other time, also we can able to uniquely specify that. But non-deterministic force are random. So over time, you cannot able to predict. So what are the random force? Like the wind or the sea waves. So that kind of force we cannot able to predict. Always they'll be changing. Okay, and that kind of random force are having some specific characteristic. We random force also will not be considering in the subject, but this random force generally will be having some statistical property. They'll be having some fixed mean, standard deviation, or other statistical property will be fixed. So based on that, we analyze a system. But in deterministic system, we'll be having force in the form of a unique value with time. So if you want to plot the force with time, we can uniquely plot it. But non-deterministic, we cannot able to plot because they will be changing continuously over time. So we solve statistical property based on that. Then when we are talking about the force, there are other category in which we can able to classify. This is another way we can able to classify. One is the periodic. Basically, this is both periodic and non-periodic. Both are deterministic. Example of the deterministic case. Periodic, you know that over certain period of time, that force will repeat. Like when we talk about the unbalanced force in the rotating machinery, that force repeats. Or when we are talking about a engine cylinder when it is moving, that particular force will be repeating over the cycle depending upon this is a 2-stroke cycle or 4-stroke cycle. The forces will be periodic in nature. With over time, they will be repeating. Non-periodic is in which the force is not changing with is not repeating with the time. Like we can give the example of earthquake. So suddenly some jerk will come, but that will not repeat every time. Okay, it will be in very short duration, and it will be non-periodic. It will not be repeating all the time. Another thing is maybe if we are blowing hammer onto a particular object, that is also non-periodic. No, that is also called transient. So suddenly applied force. So those are non-periodic because suddenly applied force will not be repeating all the time. Okay. So there are two broad category of the deterministic force. One is periodic and another is non-periodic. Another subclass of periodic is the harmonic force, which is having a single frequency, because periodic force will be having multiple frequency, but simple harmonic force will be having single frequency. Okay, so let us see this particular pendulum example, which you have already attempted earlier, but with a different perspective. So when we give a displacement to the pendulum, the weight of this is acting here. We are assuming that this pendulum is moving in a particular plane. It's not moving in a two-dimensional or three-dimensional. It is moving in a particular plane, and theta is, initially we are assuming that it's not small, it can be large also. The length L of the cord is fixed, L. Weight is acting of this bob, which is downward. Now, if we take the force component of this perpendicular to this particular line, okay, so that will be mg sine theta. Okay, and this force component will be in the direction of this, because one component will be along the thread, another will be perpendicular to. So I'm talking about the perpendicular to this. So that will be mg sine theta, because angle I'm able to check. And this is trying to rotate this particular pendulum opposite to the displacement. So you can see is pushing this side, which is opposite to the displacement. So we are writing that as minus, because of that, minus mgl sine theta. So this is the only force acting on the bob in the tangential direction, and that should be equal to rotary inertia of this bob about this point. So that is nothing but ml square is nothing but the polar moment of inertia of the bob about the O, and theta double dot is the angular acceleration. So this is a simple Newton's law in which we are writing the sum of forces acting on the bob is equal to the inertia force. Here the rotational coordinate is there. So inertia force is there is a moment, inertia moment. So now you can see that m is common, so that will go. So this equation can be written like this: theta double dot, dots are very small, plus gl sine theta is equal to 0. Now sine theta is so this is a nonlinear equation. Okay, this is a nonlinear equation because sine is a function of theta, and sine theta can be expanded like this. So you can see theta is having cube and fifth degree and other degree. So this is a nonlinear equation, is very difficult to solve. So what we do in the assumption, we say that this particular angle which we have made, or we have given the displacement, if it is small, then sine theta can be truncated. If theta is small, this theta cube will be very small, because if 0.1 is there, if you take the cube of that, it comes 0.001. So it becomes further small. So we can drop all higher degree terms, only theta will be left out. So you can see this equation will simplify to theta double dot plus g by L, theta is equal to 0. So this is a linear system in which the power of theta is 1, the degree of the theta is 1, so it is a linear system, and solution of this is we can able to find easily. Okay, this is called harmonic oscillator. Okay, so let us see. So I think if you see this G by L is nothing but the natural the I think period of oscillation of this omega square is equal to G by L, and the motion can be defined because there is a second order differential equation. So solution will be in this form, in which two constants will be involved. A and B, which we need to find out from the initial condition which we are given. So we are given some small displacement, or along with that, if you are given some velocity, so that A and B will be obtained based on that. Omega is the frequency of oscillation of that, because in this pendulum, when we are disturbing and leaving it to oscillate, it will be oscillating about with its frequency, natural frequency of the pendulum. So this is the nothing but the frequency of natural frequency of the pendulum. Okay. This A naught, A and B, as I mentioned, can be obtained from initial conditions, because we can able to differentiate this once, and then we can able to apply that at t is equal to 0, we have theta naught displacement, and t is equal to 0, velocity is t naught dot. So these are the two initial conditions of the angular displacement. Then A and B can be obtained. I think you have done this in your dynamics of machinery course, how to obtain A and B based on the initial condition. Maybe you can refer back. So based on the initial condition, we can able to get how the theta will behave with time. This can be plotted with time in a plot. So theta versus time. Okay. So, and there are different ways we can able to write this A and B, in the form of amplitude and phase. Okay. So the previous equation, this equation can be written in amplitude and phase form, like C cos omega t minus phi. So C is the amplitude, which is defined in terms of A and B like this. So this is square of first plus square of B, and square root of that, if you do it, we'll get the C. Phi is the tan inverse of B by A, and we know A and B. So phase and the amplitude. So I'll talk about the phase subsequently, or the physical meaning of the phase and amplitude. So C is the amplitude and this is the phase. Okay. So one more slide. Yeah, this slide I will complete, then I will stop here. So we know that the period of that particular pendulum is T, capital T. Natural frequency F, that is in cycle per second or hertz. Then we have the circular frequency omega, so which is related with the time period like this. So the circular frequency is nothing but 2 pi by time period, and this frequency is F is hertz, and omega is in the radians per second. So this simple relationship is there. Either we want to write the frequency in hertz or in radians per second, or depending upon that, this relation can be used. Okay. Now in the previous equation of motion which we obtained, this equation of motion, I have multiplied that equation by ml square theta dot. Okay, I'm just rearranging that equation of motion. I have multiplied by this term, and I'm integrating over time. So you can see that theta double dot was there. So ml square theta dot I have multiplied. In left side also, I brought the other term in the right side, ml g. So because g by l was there, so l square got l because it got cancelled. So I have integrated all this. Because I have integrated, so a constant term I am adding here. Now I'm rearranging these equations. Okay, so this first term is like this. This can be rearranged in the differential form like this. If I differentiate, you'll see that I'll get the same equation. If I differentiate, I'll get 2 theta dot, and then theta dot once you differentiate, so you'll get the theta double dot also. So there's the same equation as this rearranged form. But with this, what we have done, the differential operator is here. These are constant. So directly it can be integrated to this expression. Okay, and what is this expression? Half ml square theta dot square. This is the polar moment of inertia of the pendulum. This is the angular displacement, angular velocity square. So this is nothing but the kinetic energy of the pendulum. Second term, if I take, I'm keeping now sine theta as it is, not simplified in this case, sine theta as it is. So this also can be rearranged in this form. So if I differentiate this, I'll get minus sine theta and then theta dot. So you can see the same thing. So minus term is here because of that. And again, it has come to the total derivative form because this is a constant. So this will give us me mgl cos theta. And mgl cos theta is nothing but the potential energy of the system, because in due course I will explain how, if you can explain here also. Is that, yeah. So because initially the pendulum will be somewhere here when it is not oscillating. So how much it got lifted up is that expression. So mgl cos theta. So L cos theta is the distance which is lifted, and mg is the force. So it has done this much work against the gravity. So this is the potential energy of the system. But we'll go into more detail in this kind of energy expressions in the subsequent lectures. So this is the potential energy. So you can see the first term is the kinetic energy, another is the potential energy. So total is kinetic plus potential is equal to total energy. So you can see that E is a constant. So total energy is conserved, kinetic energy plus potential energy. So I'll stop here. And if you have any query, you can. Yeah, please, if you have any quick query. Nikhil? Nikhil Mishra? Any query, you can raise hand.